So, good morning, everybody. In the last class, we were discussing about the emitter follower configuration of a transistor. We have analyzed the circuit, an emitter follower amplifier circuit, and we are yet to discuss about the current gain and the output impedance. Therefore, I will continue the discussion on that. And following that, I will discuss about the FET small signal model, the junction FET small signal model. Now, going back to the emitter follower configuration. So, this is the circuit we were discussing about with this kind of biasing arrangement, and the output is taken from the emitter resistance. Now, to analyze the amplifier performance, so we formed the equivalent circuit and we got the equivalent circuit in this form. So, this is the input port and this is the output port, and the input impedance Ri dash is, as we discussed in the other configuration, in the common emitter configuration, Ri dash is going to be beta Re plus Re into 1 plus beta, and the input impedance is Rb in parallel with this Ri dash, and the voltage gain, and we obtained an expression for the voltage gain, and because the input voltage is equal to this voltage drop and this voltage, the output voltage is going to be a fraction of the input voltage, and that fraction is almost close to unity, and that's equal to 1 plus beta Re by beta Re plus 1 plus beta Re. When 1 plus beta Re is much larger than beta Re, so this is almost unity. Now, we shall continue the same discussion and discuss about the amplifier, the current amplification or the current gain. So, please note that the output current over here is treating Re as the load resistance. The output current is Ib plus beta Ib, it is 1 plus beta Ib is the output current, and the input current is this current. Now, the current gain is, so the output current to input current ratio, and that can be expressed as and I naught is known to be 1 plus beta Ib and divided by Ii. And if we know the ratio between Ii and Ib, we can substitute it here and get the expression for the current gain. So, please note that from this circuit on the input side, we can determine the ratio between Ib and Ii. Now, actually Ii gets divided between this Rb and this Ri dash, and that's what decides the ratio between Ib and Ii. So, Ib is equal to Ii into Rb by Rb plus Ri dash. So, by substituting this expression in the current gain expression, we can get the current gain as 1 plus beta multiplied by Rb by Rb plus Ri dash, where Ri dash is beta Re plus 1 plus beta into R capital E. And when this Rb is much larger than Ri dash, this is almost unity, and the current gain is 1 plus beta. That means almost all this input current goes into the base, and when Rb is much larger than the input impedance, and almost all current goes into the base, and the output current is 1 plus beta times that. Therefore, the current gain is 1 plus beta. and which is of the order of 100 typically. Therefore, you will get a current gain of the order of 100 in this configuration, whereas the voltage gain is almost unity. Now, the output impedance. So, let us derive an expression for the output impedance. Well, to look at the output impedance may appear to be large, but when you analyze it and see, you will find that the output impedance is very small. And I repeat, we define the output impedance like this. When you apply an external supply V volts here, an alternating signal, and when the input is replaced by a short circuit, the impedance looking in to this terminal is the output impedance. That means when V0 is an external supply applied, so we determine the current I0 here, V0 to I0 ratio is this. And when you replace this input voltage by a short circuit, what happens to RB? RB is shorted, therefore RB doesn't come into picture. And what happens to beta RE? Beta RE comes in parallel with RE. Therefore, if V0 is the voltage and the current that flows into RE is V0 by R capital E, and the current that flows into this beta RE is V0 by beta RE, and that current is minus IB. Therefore, the current components, let us compute these two current components. So, these two current components are, out of I0, one component is V0 by R capital E itself. The next component is V0 by beta RE plus we have one more current component, that is beta IB coming into the terminal, therefore minus beta IB. This is the total current. Please note that this current I0 is, so this current going through beta RE and this current going through RE and minus beta IB. Now, once we obtain an expression for this, V0 divided by the current I0 can give us the output impedance. Yes, please, there is a question.
So how IB has come in?
Well, the external supply which you have applied here is directly coming across RE, and the voltage drop across RE appears at the input, on the input side, because R capital E is common to input as well as output. Because of this simple reason that RE is appearing between the input and output, this RE is reflecting a voltage onto the input loop, and because of which IB is coming up into picture. So that is happening because you are applying the voltage in this fashion. Any other question? Now, please note that, so this current is V0 divided by beta RE, and that is equal to minus IB. So let us find out, use another equation. Minus IB is V0 by beta RE. So this is another equation. Now substitute this equation here. So you will find I0 as V0 by RE plus V0 by beta RE or small e, and plus V0 by RE itself, beta by V naught by small r e itself. So V naught divided by I naught gives you the output impedance, and I naught divided by V naught gives you the output admittance. Now the output admittance is 1 by Re plus 1 by beta Re plus 1 by Re. So this means that we have Re, the output impedance is Re in parallel with beta Re in parallel with another Re. So this is approximately equal to, since 1 by Re is much larger than 1 by beta Re, this is approximately equal to 1 by capital Re plus 1 by Re. So it is a parallel combination of Re and R small e. Hence, the output impedance R naught is Re in parallel with R small e. Please note that R small e is of the order of a few tens of ohms, a few ohms to a few tens of ohms. Therefore, output impedance R naught is going to be a few tens of ohms in the circuit. So that is the primary advantage of the emitter follower circuit. It offers high input impedance and very low output impedance. So here the impedance is very low. So this is equal to this Re in parallel with this beta Re divided by beta. So the divided by beta or 1 plus beta is coming because of this current source. Hence it offers you a very low output impedance. So as a result of this, we can use an emitter follower circuit to drive low impedance loads like loudspeakers in a public addressing system and motors. Any questions on the emitter follower? So please note that the emitter follower has a voltage gain which is almost unity and current gain which is of the order of 1 plus beta, except for the fraction on the input side here, the current division on the input side here, it is 1 plus beta, and the output impedance is very low, Re in parallel with this R small e. So these are the characteristics of an emitter follower amplifier. Any questions? Now we shall discuss about the FET transistor model. Before going into the FET transistor model, so let me discuss about, summarize the characteristics of a common emitter amplifier also. So please note that in a common emitter amplifier, the input impedance is of the order of 1 kilo ohm. In the common collector or emitter follower amplifier, we have high input impedance, a few tens of kilo ohms. Here the voltage gain is approximately 1. Here the voltage gain is high. So it is of the order of tens to hundreds, a few tens to a few hundreds in the case of a common emitter amplifier. And the current gain is of the order of 1 plus beta in both cases. So this is of the order of beta in the case of a common emitter amplifier, and this is of the order of 1 plus beta, which are almost same, and it is typically 50 to 100. And the output impedance here, when you use the accurate analysis, the output impedance is RC in parallel with that R naught, which is 40 kilo ohms typically, and here the output impedance is RE capital E in parallel with R small e, which is approximately R small e, because R capital E is of the order of few hundreds of ohms to a few kilo ohms, and R small e is of the order of a few ohms to few tens of ohms, therefore it is of the order of R. So this is the comparison between the characteristics of a common emitter amplifier and common collector amplifier. The advantage here is it gives you both voltage gain as well as current gain, and because of which reason the power gain is high in the case of a common emitter amplifier. Whereas in the common collector amplifier, the current gain is present and the voltage gain is almost unity, but it has a very interesting characteristics that it can be used for matching the input circuit as well as the output loads, input sources and output loads. Now, having discussed about the transistor amplifier small signal model and the analysis of amplifiers using that model, we shall now discuss about the small signal model of a JFET, junction FET. So this model comes from the characteristics of the field effect transistor itself, like the bipolar junction transistor. And this is useful for us to analyze the amplifiers and determine the performance like voltage gain, current gain, input impedance and output impedance. Now, if you look at the FET characteristics, you will find that it is a current control device. So input side voltage VGS decides the output current ID. When you operate the quiescent, the FET at certain VGS, it will give you the corresponding ID. When you operate it at the Q point VGSQ, it will give you the Q point ID. And now, so depending on the ID here, so the output side so this ID is a function of this VGS. And depending on this ID cube, you have that current flowing in the circuit. And if there is an external resistance RD, and that is responsible for providing some VDS, drain to source voltage. Now, how much current flows into the gate in a field effect transistor? Because it is a reverse biased PN junction, very small current, that is the reverse saturation current, flows through this. For all practical purposes, you can treat it as zero current. So even when you apply an alternating signal over here, still this bias potential plus the alternating signal put together, still it is reverse biased. Therefore, for small signals, still it is reverse biased. Therefore, the current is negligibly small. Hence, the input side of a field effect transistor, this is the input side. So on the input side, it is an open circuit. If this is gate and the source is connected here, on the input side, so whatever is the signals that is applied, once it is a small signal, its amplitude is much smaller than the VGS Q, the Q point gate to source voltage, then this is reverse biased and it is like an open circuit. This is like an open circuit. So the input impedance, the field effect transistor offers is infinity for all practical purposes. So the field effect transistor doesn't load the source. Now does this VGS matter? This Vs matter? So this Vs causes some change, this Vs plus VGS, so causes some change in the voltage, gate to source voltage, and you will have a corresponding ID, change in the ID. And this alternating ID, so that is this ID for this Vs around the Q point is responsible for an amplified voltage drop across this R capital D, across the drain resistance. So typically, what is the behavior here? The gate to source potential is creating a changing output current. That means on the output side, there is a current source whose amplitude is controlled by the input voltage variation. Hence, we have here on the output side a current source whose value is given by, whose value is proportional to VGS, and the proportionality constant has units of conductivity, then if we call it as GM, so this current, output current ID, I am talking about only the alternating current, and this current is equal to GM VGS between the drain and the source, and this VGS is related to, so the gate to source potential. Therefore, this is the simplified equivalent circuit of the junction FET. Now, how do you get GM-VGS? There is a resistance here, output resistance, the channel resistance comes into picture. I will discuss about it a little later. Now, how do you get GM? So, looking at these characteristics here, so please note that if this is the VGS or Vs, that is the voltage applied, alternating voltage applied, and that is responsible for this alternating current. Now, how much is, now VGS is this GM is the ratio between this ID, that means alternating ID, divided by this voltage, and that's nothing but slope of this characteristics at the Q point. Slope of this characteristics at the Q point. So please note that this equation has this kind of relationship. ID is IDSS into 1 minus VGS by VP whole square. Now, if you differentiate this with respect to VGS, you will get the slope of that equation. Therefore, GM is equal to 2 IDSS by VP into 1 minus VGS by VP. So this GM with a negative sign. And now with a positive sign here. Now, please note that this GM is a function of VGS. If the Q point is somewhere here, please note that the slope is different from when the slope of this point here. Therefore, it is a function of the VGS. Right, that's right. Mod Vp into 1 minus VGS. So GM is equal to this at VGS is equal to VGS Q. So it depends on the VGS Q, the Q point. Hence, so this is equal to this relationship. Now, if you treat the slope as GM0 at this point, at 0 current, please note that this becomes GM0. And this equation becomes GM is equal to, so GM0 into 1 minus VGS by Vp. Where GM0 is the conductivity at this point. There is a slope of this curve at this point. And this GM is known as the transconductance because it is the conductance between an output current and the input voltage. It is a transconductance. It is known as transconductance. And it is of the order of a few millimole. GM is of the order of a few micro mos to a millimos. Now, let us look at the output characteristics. The output characteristics is something like this, depending on the VGS Q. So this characteristics is for VGS 1. This is say VGS equal to 0. This is VGS 1 and this is VGS 2 and so on. And this is between the drain to source voltage and this is the drain current. Now, is the drain current constant with respect to VDS? If you look at it microscopically, you will find that so these curves have some slope. If there is a change in the VDS, so it will give some change in the drain current. So a delta VDS gives you a delta ID. That means the output current is affected by the voltage change here. The current is affected by the voltage change here. What does it mean? It means that there is some output resistance or output conductance. And the symbol used for this is the lowercase r d. I repeat, when you connect a load resistance here, depending on the load resistance, if the load resistance is large, this GM VGS flows through that load resistance, and you will have a large voltage drop across the load. If GM VGS is low, that means the current is low, the output voltage is low. Now the question is, so does the current get affected by the load? If it is an ideal current source, so it doesn't get affected. If whether it is a large resistance or small resistance, the same current flows through this. But here we have seen that with the voltage the current varies slightly. That means depending on the resistance here, the voltage here depends on how much resistance is used, and depending on that this current varies. Hence it is clear that there is a resistance in between this, because only when there is a resistance in parallel with this voltage affects the total current flowing into the load or out of the load. Hence the source is not an ideal source, and it has a resistance parallel to it. And the value of the resistance, so naturally depends on the variation in the current that takes place because of the variation in the voltage, and so that RD is given by this delta VDS by delta ID. Because from the current source, practical current source discussion we carried out earlier, please note that whenever you have a delta ID occurring because of delta VDS, so you have a parallel resistance equivalent, and that resistance equivalent is given by delta VDS by delta ID. This was discussed when we were discussing about amplifiers, small signal amplifiers and their classification. The same reasoning applies here, and you have RD coming into picture here. And the value of RD is a few tens of ohms to a few hundreds of ohms. It depends on where the operating point is. If the operating point is here, RD is very large, and if the operating point is here at small VGSs, then the RD is small. So it ranges between tens of kilo ohms to hundreds of kilo ohms. Hence the complete circuit, the equivalent circuit is as given here. It is an output current source whose value depends on the input voltage, and there is the input impedance here is infinity, and there is an output resistance RD which can be obtained from the characteristics like this. And the proportionality constant between the output current and input voltage GM can be obtained from the input characteristics, the transfer characteristics like this around the Q point. So this is obtained around the Q point. So in this fashion, if this is the VDS cube, and so the in between value here is IDS, IDQ, then around this the slope of this curve gives you 1 by RD. Any questions on the small signal equivalent circuit of the junction field effect transistor?
So how will we show if we want to show the small means we want to show the effect of high input impedances. So here we are assuming infinity. So how will we show if we want to show that high value?
What is the question? It's not clear.
So in the small signal analysis,
Right.
if we want to show the high input impedance, how will we show that?
So it is by an open circuit. If it is infinity, it's an open circuit. If it is a few hundreds of kilo ohms, you show a resistance, and its value is hundreds of kilo ohms. Whereas in this case, it is hundreds of mega ohms in the case of a silicon junction field effect transistor. For all practical purposes, this can be treated as infinity. So just show it by resistance. And I have opened it because it is infinity for all practical purposes. It's clear? Any other question? Questions? This is a simpler circuit than the BJT equivalent circuits. Therefore, when you use this in the amplifier analysis, the analysis turns out to be simpler than the BJT analysis.
Sir, GM has been defined as a derivative of ID versus as dID dVGS. So then how come we take ID is equal to GM VGS in this model?
This is the question is how come we can take GM VGS as the output current with respect to VGS, whereas this is the derivative of the characteristics. Please note that we are now discussing about the small signals. We are not discussing about the static characteristics, that is the quiescent voltage and currents. We are now discussing about small signals. And please note that the small signal, with small signal, the instantaneous gate to source potential is equal to VGS Q plus some small delta alternating signal. And here you will get an IDQ plus some small delta as an alternating current. And we are no longer interested in the quiescent voltage and currents. Once the circuit is designed for a particular Q point, that part is over. Now we are interested in the response for the alternating signals. That is the gain for an alternating input voltage and the gain for alternating input current and so on. Therefore, we are interested in ID to Vs ratio, this ID to this Vs ratio. So please note that this ID is this deviation in the drain current here, and this Vs is the deviation in the biasing voltage over here. Hence, the ratio between these two is the derivative of this and this. A small excitation here to small excitation here ratio. Small deviation here to small deviation ratio. So that's why we are discussing about this. Even this is even valid for the BJT analysis. There also, please note that we have got Ri as the derivative of the input side characteristics. The derivative of the base current with respect to Ri as the derivative of the base to emitter voltage with respect to the base current. So the same reason is applied there also. Any other question? If there are no questions, I'll stop this lecture here, and I'll discuss about the BJT, the JFET small signal analysis in the next class.